So, welcome again. We are now into the main course after the introductory lecture. So, I hope I have been able to excite you about the application of the subject that is transport phenomena to metals and materials processing. And as I said, it is a very important subject, so we have to study it very seriously. And now we get into the first segment of the course, and that is the fluid dynamics. So, during the next 7 lectures or 7 contact hours, so we will be discussing mostly fluid dynamic principles. I will not be able to derive equations or discuss at a very extensive scale, because as you all may be aware that on fluid dynamics there could be not just one, a full-fledged several semester long courses on diverse topics, and we are trying to do everything in 7 lectures. So, which means I have to really compress the things very hard. So, we will split as per the dictate of the department that 5 lectures I will try to quickly brush up the underlying principles which are of importance to us, and then 2 lectures I will be devoting which I call as tutorials, and mostly trying to solve 1 or 2 problems and show you the tricks that how to solve the problems of general interest. Now, we have 2 words here, fluid dynamics, and the moment I say fluid dynamics, you must immediately gauge that I am talking of a fluid in motion. So, gases and liquid in motion, and why the subject is important? Because if you look at our furnaces, ladles, reactors, we all have gas and liquid flows. Does not mean that we do not have solid flows also, but that is a different paradigm altogether. So, we have frequently we frequently experience fluid dynamics or fluid motion in our reactors, gas and liquid flows, and that is often we want to know the velocity, or we want to know the pressure drop, or we want to know the frictional losses, etc. And it is by understanding the laws of fluid mechanics we will be able to extract those informations which are very vital as far as engineering exercise is concerned. Now, when we say fluid dynamics or fluid in motion, we must understand that motion is the net result and the cause is the forces. So, it is various kinds of forces that acts on a fluid element, and that causes the fluid element to move. So, in order to study the motion of fluids, we have to really look at the cause very carefully. So, we have to study forces, and you must understand that forces are nothing but rate of change of momentum. Okay? So, whenever there is a net rate of change of momentum, we say there is a force which is acting on the fluid element, or otherwise if the fluid is moving at a constant speed, we will be saying that there is no net force acting over the particles. So, many of you may have heard the term called terminal rise velocity of a sphere, or in mineral engineering context, and there you can see when you say terminal velocity, that means the net forces acting on the element is equal to 0. So, it is by considering or looking at the forces through an appropriate framework, we will be able to find out that how the forces really manifest in terms of motions. And when you do forces, and forces are vector quantities, so as the momentum, and momentum is basically a conserved quantity. So, we develop frameworks which are based on momentum conservation. We must understand when we discuss momentum conservation, it is not alone momentum conservation that we are concerned with, simultaneously we are concerned with mass conservation, that you all also must be knowing. So, it is through the framework of momentum conservation that we can establish equations or expressions which can be further explored or studied in order to understand that what could be the velocity field, what could be the pressure drop, what could be the frictional losses, etc. in a reactor containing fluids. Now, to illustrate this, how such a framework is developed, and all of you may have heard that we can start with a shell balance equation, for example. Shell balance basically implies that we take a small little volume element within the domain of interest and then perform balances or conservations of momentum, for in this particular case, how much momentum is coming in and how much momentum is going out. And then we can cast the entire thing in the perspective of the Newton's second law of motion, which states that the net The mass times acceleration is equal to the sum, algebraic sum of all the forces. And we also know there are different kinds of forces which could be acting on fluid elements. Some force could be surface forces, some could be volume forces. For example, gravity is a volume force which acts when fluid flows from a region of higher altitude to a region of lower altitude. Pressure, on the other hand, is a surface force. We can have various kinds of force, and which we will explore. For example, if you go to an induction furnace, you will find that there are electromotive forces which are acting on the fluid element. Yesterday, I talked about the surface tension driven flow in the whirlpool, and that surface tension driven flow basically can also be one of those forces which are accommodated in the expression of capital F, which I have written here. So it is by considering the Newton's second law of motion, a framework can be developed through which we should be able to analyze the flow phenomena at a quantitative scale. Now, let me explore this further and try to discuss a problem with reference to say continuous casting. Now, you know that in continuous casting we have, for example, I am depicting a slab, and those of you who are not metallurgists may know that continuous casting essentially is a process of continuous conversion of liquid steel into solid product. Here we have a mold, and the mold goes like this. It is an exaggerated figure. So this is the slab that is talking about, and what could be the slab? This width we are talking about is about 1200 meter or 1200 millimeter or 2000 millimeter. On the other hand, the thickness of the slab could be about 500 mm. It's a conventional slab, 500 mm or so. This is the outer boundary of the mold wall, and because the mold, it is a high temperature operation, tends to expand, and because of solidification the ingot shrinks, as a result of which a gap is created between the ingot and the mold. And it's through this gap that we have a flow of lubricant or fluid which is actually resting over the surface. So it is all over this area which is filled with liquid mold powder, and actually the mold powder is sprayed over the surface. So this is the top surface, and this is the direction in which the mold ingot or the casting is really drawn. So whatever is the pink shade here, that represents basically the mold powder or molten mold powder, which acts as a lubricant between the mold wall and the solidifying casting. This is used just that the metal, solidifying metal, does not stick with the copper mold. It is a very cold mold, much lower temperature. The surface temperature here is 700 degrees centigrade. It is here about 1000 degree or maybe 1200 degrees centigrade at the surface, depending on the location. So there's a tendency of sticking, and to prevent that sticking, we have mold powder that flows in the gap between the solidifying mold. Now, this more or less flows like a thin film. What is the distance here? We are talking about the film is about 0.1 centimeter. That is of the order of 1 millimeter thickness. That is the film which acts as a lubricant. So we add solid powder. That solid powder has low melting point. Because of the heat available, it melts, and that the entire thing is moving, and the expansion and contraction creates the space. The film flows inside. Now let me say that I want to now study the flow of the film, making some very simplifying assumptions. Okay? Let us not concentrate on this part. Let us not concentrate on the bottom part. Okay? Because these regions, as I will discuss later on, are called the beginning and the end. These are called the entrance regions, far away from the entrance region, far away from the exit region. So let us say that we want to look at what is happening really in this small tiny volume element that I have drawn. If I can now exaggerate this figure, then I would say that, look, this is now my mold wall. This is my solidifying casting, and this is the space that is filled with my molten slag powder or molten lubricant. These are low melting point powders that is sprayed over here, contains calcium oxide, sometimes contains silica, alumina in various proportion, and they will melt to form the lubricant here. And the entire lubricant thing is going down, and it goes down because of the fact that the casting itself is going down. So as you all know, for example, when a train moves, we see that the wind along with the train tends to move. So as the billet or the bloom or the slab tends to move downwards, it tries to drag the liquid film down, and as a result of which what happens? It flows downward, and this motion which is induced in the film is because of drag, so we called it a drag-induced motion. Also, because there is a gravitational force acting, we will see that there will be a natural tendency even without the motion of this strand. The powder or the molten powder will tend to move because there is a net gravitational force acting. So, therefore, the powder continuously moves from the mold surface, it enters here, and then through the bottom surface the powder in the solidified form again will exit. It is a very complex process, but let us not bother about the intricacies of continuous casting. Let us just treat this problem as a typical film flow problem between one moving and one stationary surface, and this represents the stationary surface. On the other hand, this represents my moving surface, and my domain of interest is in between the two. When we address any such problem, we must understand that we have to label the coordinate axis. That is extremely important for us, and I say that, let me say that this represents my z direction, and the way it is shown here, and this represents my y direction. So, this is, and what you do not see is the depth. This part is not seen here, which is basically the width of the mold which I have designated. So, it is a frontal view of the setup where you can see the film, and this film may be having a width of delta sub s. And in that, I have drawn a control volume here, and I want to do how much momentum is coming in and how much momentum is going out. So, here it says that rate of change of momentum, okay, net rate of change of momentum is equal to the sum of the forces which is acting. So, if I can develop this in word, I can say that momentum out minus momentum in and is equal to net forces, or I would say sum of all forces here, sum of all forces. Since all of you have some exposure to either heat transfer or fluid flow at your undergraduate level, so I may not sometimes write very explicitly, I wrote momentum out, but this essentially means rate of momentum out from the control volume that I may not spell out, and I expect that you will understand even by writing these simplified forms. So, momentum out minus momentum in is equal to sum of all the forces. We must understand, let us say that there is a velocity, and the velocity we say that this is the x direction, z direction, then there is a velocity here called uz. In this domain, you can expect that this uz, okay, it could be a function of z as well as it could be a function of y also, which is this particular direction. So, the x direction is the depth direction which I have not shown, and the width span of the x direction is L, as I have indicated in this figure. So, we can say that there is a momentum exchange coming into this control volume, okay, because there is a net flow. So, momentum comes in, momentum goes out. Similarly, since there is a flow here, the fluid is moving, and along in this direction also there is a momentum input, and the mechanism, even though we may not have a second component of the velocity, the momentum gets input into this control volume because of the flowing motion, as we know, because of the property of the fluid which we call as the viscosity. Okay? So, there is a shearing action as the fluid is moving. It tries to drag in, pump in momentum into this control volume, and as a result of which what happens, because of the shearing action, some momentum goes into the system, and this momentum we are talking about x momentum. There is no y momentum in the system, there is no z momentum in the system. It is a unidimensional scenario. There is a predominant x directional motion into the system. Okay? So, there is no uy, there is no ux, there is only uz. So, there is only one scale of momentum, but this momentum can get into this in this particular direction because of the movement of the fluid, and that you all know that we designate that by shear stresses acting on the fluid element, which further we express in terms of Newton's law of motion or Stokes' law of motion, okay, depending on the dimensionality of the problem. So, therefore, on the momentum out and momentum in turn, you can expect that I can have one component along the x direction, net component, because one is going out, other is going in, other is going out. So, if you subtract from one from other, I will have a net component along the x direction. Similarly, I will have a net component along the y direction. So, there are going to be two terms here. Okay? Similarly, sum of forces, when I will talk, there is a gravitational force acting over the system, and that gravitational force is directed along the z direction. So, it will be taken as a positive gravity forces, and similarly, there is going to be a pressure gradient, okay, acting over the system, or pressure forces acting over this control volume, and that will also be acting in the positive direction because there is a net motion in this particular direction or along the z direction. So, the sum of the forces will have two components. I write it as on the left hand side we will have two components, on the right hand side net we will have also two components. So, first component is, I repeat again, the net effect or transport of momentum along the x direction, or this is used in the conventional terminology as a net efflux of momentum along the x direction, or net efflux of x momentum along the x direction, net efflux of x momentum along the y direction. The term on the right hand side represents gravitational force, and the second term represents the pressure force. So, we can establish now a formalism, okay, or a framework where we will have two terms on the left hand side and two terms on the right hand side. In the process of finding out this, there is an approximation which we normally apply. Suppose I say that this represents the delta z of the control volume, and this represents delta y of the control volume, the span of the control volume, and this delta x and delta y are really very, very small. So, they are tending towards 0. Now, there is a hypothesis that when you try to approximate, find out the net effect, okay, subtract one from the other, we can approximate the value of a dependent variable phi, for example. So, you can say this is phi, any value phi. Phi could be momentum, phi could be viscosity, phi could be anything, okay, any parameter. Phi, we can say if it x and then this, sorry, this is z, and this phi is z plus delta z. So, the value of phi evaluated at z, which is in this case 0, and then the z value of phi evaluated at z plus delta z, so 0 plus delta z essentially. The value at z plus delta z can be approximated as phi at z plus delta z. We can say that this is going to be approximated as phi over dz. This is called a linearization. Okay? So, if we know the value, therefore, so I can say that if you now subtract, for example, you have z is equal to z plus delta z. So, similarly, if you subtract this from phi z, and then you can get the net effect, for example, and that will give you so it is going to be phi z plus this. That's what is the net term. Okay? So, now if you bring this to the left hand side, in that case I can take this out. So, as a result of which I can say this will come out to be this particular expression. This is the result of the linearization, and we basically say that when delta x, and this is delta z, tends to 0. Because you see, if you have, this is a linearization, and the linearization essentially means that when you have, no matter what is the nature of the curve, you cannot approximate this curve, okay, which I have drawn with a red pen, with a straight line. This is going to be a rigorously erroneous. It's a very erroneous scenario if you try to approximate it. But imagine if the curve is very small like this. In that case, it is a good approximation to do it because the segment size is smaller and smaller. So, therefore, no matter what is the actual nature of variation of phi, you can present the phi in a linearized fashion with regard to the original phi value at the preceding station through these expressions which is valid only when delta z, because our control volumes are very, very small in the system. So, that is why we should be able to write down. Okay? So, therefore, the net effect here can be actually, now the momentum is what? The momentum basically is, I do not have to derive all these things because otherwise it is going to take enormous amount of time, and I have to do everything in 5 lectures. So, you know that rho ua, where rho is the fluid density, u is the velocity, and a is the area. This represents the mass flow rate. So, if you multiply this with another u, you get what? Mass into velocity. So, that becomes mass flow rate into velocity. So, that becomes momentum flow rate. So, momentum flowing into the system or flowing out of the system. So therefore, we can say that now if we say rho ux into area, and what is this area? This area over which, through which it is coming in, x, okay? And in this case I would say not x because it is z. So this multiplied by delta y, and the area is delta y into L. That is the area through which the fluid is coming in, and that we can say that this is delta y, okay, into L. This is the value of momentum evaluated at this particular. So this value at x, z, z is equal to at z, and then we have, this is what? This is input. And then we can say the output is going to be equal to rho uz, the same area is there, and this is going to be at z plus delta z. So the moment we do the balance, input minus output, okay, or in this particular case momentum out minus momentum in. So we are going to have what? The moment you use linearized, this term is going to be equal to this term plus the additional derivative term that I have written there. So therefore, on the first term that I am going to get here is going to be essentially delta z, delta y, and m. That is the term I am going to get. Similarly, we can get, if you do the same exercise, we will get the same term, we will get some the second term, this is the first term, and the second term similarly I am going to get the shear stress, because we are talking about the momentum transport along the y direction through shearing action. So I will say that this is going to be now yx. This I am going to explain to you what does the notation essentially implies, and this again now is going to be delta x or delta z multiplied by delta y multiplied by L. That is going to be. So output is greater than input, so that term is positive. Output is greater than input, so this term essentially represents second term. So this, if we sum this up, we get the left hand side, and then on the right hand side we can have the pressure, we have rho, which is the density of the fluid, then we can have acceleration due to gravity, the component of it is gz. This essentially implies that gz is equal to 9.8, okay. It is not in this direction, so it is a positive value, so gz is to be substituted as positive 9.81 in SI unit, okay. And then we have the pressure gradient term, and that pressure gradient term is again going to be, and this is to be multiplied by delta y delta z into L, because it is rho, the net force is going to be is a gravitational force multiplied per unit volume, so you have to multiply it by volume so that we get force. So these are all net rate of change of momentum. So every term here will have the dimension of force, or which is like Newton, okay. And therefore we have here also delta x, delta z, delta y, and L. So this term delta z, delta y, delta x cancels out, and then we have an equation now with the four terms. But now I want to introduce here, before I sum this up and present the whole thing in a compact fashion, I would now like to introduce that, well, I have written a momentum conservation expression, okay, from Newton's second law of motion. Now I would like to introduce the mass which is coming into the system and mass which is going out, that the mass conservation is to be. Now, as I have indicated, that mass coming into the system is what? The mass coming into the system is rho ua. You must understand that since there is only uz into the system, no uy and no ux, so therefore mass can only flow into the control volume, okay, along the x z direction itself. So therefore I can say that if we again do the same, mass coming in here minus mass going out here, or the way we have written as per our convention, mass going out minus mass coming in, then what we are going to get? We are going to get an equation something like rho times uz times is equal to 0. There is no second term, because in this direction no mass could flow, because there is no velocity here. Okay? The momentum is flowing, but the mass is really not. So, therefore, we have in this particular case, the moment we see this, we find out that this, there is uz, okay, is not a function of z. So, the mass continuity gives us a very, we would like to say sir has drawn a two-dimensional domain. So, I would initially expect that the velocity field is a function of or dependent on both x and y. But in this case, the moment we apply the mass continuity equation, okay, we see that in the one-dimensional context, it tells us that there is no variation of the velocity along the z direction. What does it indicate? That there is no net acceleration along the z direction. That is what is the implication of this. If this is so, in that case, this term will vanish, and therefore, the equation will be now, the first term will vanish, this will disappear, and this will disappear because of the application of the mass conservation equation, and therefore, we will be left with three terms, and that is going to dictate our momentum conservation equation. Given this background, now I will represent the momentum conservation equation in its final form. So, I have to erase the board and then do it for you. So, on the left hand side, I will have one component that will come out from the lateral direction momentum input because of the shear stress itself, and this is going to be, that is the term which will be left on the left hand side, and on the right hand side we will have the gravitational force plus the pressure gradient. At this stage, we can apply certain constitutive laws by which we should be able to replace this shear stress. Now, this shear stress, as I have indicated, that it has the same dimension. Shear stress is what? Force per unit area. Now, if you take the momentum flux also is what? Momentum and then flux, that means it is time and it is unit area. But momentum is mass into velocity, but velocity by time is nothing but acceleration. So, mass into velocity by time is force. So, velocity by time is acceleration, mass into acceleration is force, and force divided by area is shear stress. So, it is one and the same thing, depends on how you want to interpret it. So, this is the flux of momentum because of the shearing action along the y direction, and this is balanced by the forces. We must understand that since there is no acceleration here, in that case the pressure gradient is expected to vanish, and that I will show you in a minute. So, this shear stress, now we can have if you want to calculate not the shear stress, but the velocity, in that case the shear stress must be replaced by a suitable expression, and here we bring in what is known as the Newton's law of viscosity, which is applicable and this is valid typically for parallel flows, one-dimensional parallel flows, where we can write that the tau yx is equal to minus mu. So, this is going to be actually not, and this is y, yes. So, this is going to be not y, and this is not x, there is x is on the other dimension, sorry. So, you can, so tau yx is equal to z is equal to the gradient of the velocity along the y direction. Now, this essentially represents, actually as I said, it is momentum flux. So, what we are going to see, this is which momentum? This is the z momentum, And in which direction I am talking about the transfer of z momentum? Along the y direction. So, the transport of z momentum along the y direction, that is what is this term, and this tells us that this is equal to a proportionality constant mu, which is a state property. Given that temperature and pressure are constant, we can use a constant value here, which is the dynamic viscosity of the fluid. The unit of mu, as you all know, is kg meter per second in SI unit. That is the, we write it like this, mu, and this represents the unit of mu, and this represents the corresponding velocity gradient. Now, if you have a multidimensional equation, suppose you are doing not an energy momentum balance over a element like this, but over a real three-dimensional element where you have flows in all directions. In that case, there would be other velocity gradients also which will be meaningful, and then you will have additional term, and those expressions we call as Stokes' law in fluid mechanics. So, the stress, or in general we can say that this is stress. Also, this term can be interpreted as strain. What is the dimension of strain? Strain is centimeter per centimeter. Okay? Change in length per unit length, that is how we define. And the rate of strain is change in length per unit time, and that is what it is. And here if you see, this is meters per second, this is meters. So, this is a dimension of 1 by meter. So, this basically is strain rate. This essentially tells us in the fluid, the model Newton's second law of motion, Newton's law of viscosity that I have written, the stress is directly proportional to the strain rate. Here I want to introduce one thing which you may be knowing, that it is not always necessary that stress is proportional to strain rate to the power 1. It could be a different exponent altogether. Okay? So, it could be different from 1. In this case, stress is proportional to strain rate to the power 1, but this 1 is not sacrosanct. We say that if this relationship is obeyed, stress is proportional to strain rate to the power 1, then it is a Newtonian fluid because it obeys Newton's law of viscosity. On the other hand, if it is not 1, if it is different than 1, then we call it is a power law fluid. For example, plastics, polymers, etc. do not obey Newton's law. Some people say even our slags also under certain composition rates do not obey Newton's second law, but the metals certainly are Newtonian liquids. So, with metals and gases we should be able to consider the Newton's law of motion fairly applicable. So, the moment we substitute this, we get an expression, okay, by using the Newton's second law of motion. So, we can get that and if we take it to the other side, then we get plus rho g plus del p del x, and that is good. That represents our momentum conservation expression in this particular case. Now, this time is constant here, rho g. Now, let us look at del p del x. You can imagine the continuous casting mold that I have drawn when I first started the lecture here. Right at the top, the pressure is the atmospheric pressure, and at the bottom of the continuous casting mold, it is also exposed to the atmosphere. So, throughout the pressure is actually the atmospheric pressure. Of course, the static pressures are different at different heights because the fluid has certain weight. So, therefore, we can expect that in this particular case, there is no pumping of fluid, etc., so that there is no really pressure gradient that develops here. So, the pressure on this surface and the pressure on this surface of the control volume are really expected to be equal. There is no pressure gradient because at the top surface the pressure is 1 atmosphere, at the bottom surface also the pressure is 1 atmosphere. So, this term can be. So, now what we have got? We have got a characteristic, okay, differential equation, second order homogeneous differential equation, okay, and here we have a constant term here, and the moment we integrate, we can imagine that if you write down, this is a simple task. So, if you have yes, so if you if you write down, this expression, if you take it to be is equal to 0, in that case, okay, let me just, so that you can see my board work clearly, okay. So, I can say that this is and you can immediately gaze that the solution of this will come out to be a parabolic equation because this is constant. The moment I take this term is equal to 0, the solution of this differential equation will come out to be a straight line equation, okay, that you have done. Those of you who are exposed to heat transfer courses, when you have Fourier's law of, of heat conduction that is embedded into a conservation framework, and you have the Laplace equation, and the Laplace equation with no source term gives you a straight line temperature profile, steady state temperature profile between the 2 points. And similarly here also, if you take away this term, the velocity profile between this and this is going to be linear. On the other hand, if you just, if you retain this, we will find that it is non-linear or a parabolic velocity profile. Now, because it's a differential equation and it's a second order equation, so 2 conditions are necessary, and those 2 conditions in this case are with respect to y. If you look at the mold wall, of course, in reality the mold is stationary, non-stationary. It really makes up and down movement, which we call as a reciprocating movement of the mold. Continuous casting per se is an extremely complex process, and I think it is perhaps too simplistic to try to put continuous casting film flow problem within this kind of a framework and then write down. But this is just for the sake of illustration that I wanted to, I could have given this example from other areas also, and have taken a film flow of water over a flat plate or something like that, but I decided that I should do it in the context of continuous casting so that it appeals to all of you, nicely, because you are our metallurgical engineer by profession. So, because it's a second order equation, so we require 2 conditions with respect to y. Boundary conditions are, you remember when you solve differential equations, you get constant of integrations, and those constants of integrations needs to be evaluated from boundary conditions. And in this case, the boundary conditions are, this is at y is equal to 0, and as I have indicated, this is film thickness and this is at y is equal to delta S. So, y is equal to 0, the fluid is in contact with a stationary surface, and that is why I say that the uz must be equal to 0 at y is equal to 0. This is called typically a no slip boundary condition. The fluid cannot flow past a stationary surface, it requires an infinite stress. Similarly, we can say uz is equal to the casting speed. Again, no slip boundary condition. If the plate is moving, casting surface is moving with a certain velocity, the layer of fluid which is in contact, fluid means in this particular case the liquid slag which is in contact also moves with the same. So, if we say uc is the casting velocity, capital U sub c, so at y is equal to delta S. So, now the problem is defined. So, you remember we have to draw a figure, we have to draw the coordinate axis, we have to label in which way the velocities are, in which direction, z direction velocity is uz, y if there is a ui velocity, so we will write it ui, then we will write down the differential equation, then we will write down the boundary condition, and that makes the statement of the problem complete. Now, we got to solve this equation, it is a piece of cake, we need not, so we integrate once, we get one constant of integration, we integrate twice, and then we get, the final expression. And I will just take out a note from my pocket and write down that what is that final expression which one can obtain by integrating. So, the final result after integration, that is after we apply the boundary conditions, and we can say that the uz, and as you can see uz now is a function of y only. It is not a function of x because the mass continuity has told us, and if you integrate it, it has 2 different terms because there are 2 different constants of integration. I am casting into y divided by delta S plus rho g by 2 mu into delta S into y minus y square. That is the solution of this equation, which tells us that the flow of the film along the z direction is related to two different components. This comes from the drag effect, that is, because the strand is moving down, it is trying to drag fluid along with it, and it is also moving with regard due to the gravity forces. So, the presence of g on this term. So, this is the gravitational component of the motion, and this is the drag component of the motion. Okay? And now, we can say we can do many things here. We can find out an average velocity. An average velocity means the velocity through the, if the film is like this, okay, the casting is moving in this direction. So, there is a velocity which is a function of y. So, the velocity here is 0, the velocity here is maximum, which is the casting, and from here to here the velocity changes, okay, and the changes may not be, no, this is not right, the changes may be something like this, okay, because of the nature of this graph. So, as you can see, the velocity is a function of y as we it changes from 0 to the maximum value, and this we can have now a cross-sectional average velocity, for example. So, all this, suppose if we say, I will explain that suppose I take, a square sample, and I say, look, I divide it into 4 parts. One has equal parts, one has 200 degree, one is 300 degree, another is 400 degree, another is 500 degree. If all the parts are equal, what is the average temperature? You will simply sum this up divided by 4. But imagine if these are non-equal parts, in that case you have to really do an integration, okay, and then find out, and that integration basically is, if you take t, and it is going to be t dx dy, okay, and that is going to be dx, which we call as a area average temperature of the square plate that I have written here. Similarly, since the velocities are different at this point, we should be able to now integrate the velocity as a function of y, remove the dependence on y, and have a comprehensive velocity scale, and that average velocity can be given uz average. So, I would say that average velocity is by definition is uz, which is a function of y. Then I integrate this uz over dy, okay, because uz is a function of y, and then I say that it is cross-sectional area. So, I would say that this will have a limit of 0 to delta. Using the same philosophy, therefore, from the you have obtained this expression that I have given here already. So, the uz as a function of is known. So, this is equal to uc, as I have written, y by delta s plus 2 mu gd into y delta s minus y square. This is the expression that I have written. Now, I want to find out what is uz average, and for that I have to integrate 0 to delta s. So, that is the expression of the cross-sectional area average. So, area average, which area? It is the cross-sectional area, and L ds represents the cross-sectional area. If you remember that L is the depth and ds is the film thickness in this direction. So, L into ds represents the area. So, it is area here, and the moment you look at this, it is dimensionally consistent, because L into dy integrated will cancel with L into ds. So, the dimensionality on the left hand side is velocity and the right hand side is also velocity. And if you integrate this, then let me go to this section again to write out the final expression, and the final expression I can write down for uz, again I will copy it from my notes, and that uz average can be, after doing that simple integration, okay, it could be given as u casting divided by 2 plus rho g delta s squared divided by 12. I can find out the mass flow rate also, which is equal to rho times volumetric flow rate, which is Q. What is the definition of volumetric flow rate? The volumetric flow rate is nothing but the average velocity into the cross-sectional area. So, the moment we multiply this value with the cross-sectional area L into delta Z, we will get what is known as the volumetric flow rate. So, Q dot is equal to average velocity multiplied by cross-sectional area. That is the definition. So, average velocity expression I have already given. If I multiply this term with L into delta y, in that case I should be able to L into delta S, I should be able to get. So, therefore, I would say that if you multiply it with L and if we multiply this with delta S, so L times delta S represents the cross-sectional area. So, you will change it this, and then this term I should be able to change it now. If I do not write L, in that case I would say it is the volumetric flow rate per unit depth of the slab. That is what is the expression. Now, you can look at the beauty of this. So, I can do a simple exercise in the industry based on this formulation here. Casting speed values, for example, I know it is of the order of 1 meter per minute. Let us, you can check that this equation is consistent here. So, we have centimeter per second into centimeter into centimeter. So, this term is centimeter cube per second, which is nothing but the volumetric flow rate. Similarly, if you take this term here, so this term will also come out to be centimeter cube or meter cube per second, which is also has a dimension. So, it is a dimension of meter cube per second, this is a dimension of meter cube per second, so that the equation becomes dimensionally consistent. Now, in the industry, for example, so if you look at the value L, as I indicated, it could be about 1200 mm or 1 meter, 1.2 meter. If you look at the value of casting speed, this could be 1 meter per minute. So, it is about 1 divided by 60 meter per second. I have already told you the delta S value is about 1 millimeter, or which is equal to 10 raised to the power minus 3 meter. What other parameter is left? Mu, which is the viscosity, rho is the powder density. It is not the steel density, because we are talking about the flow of the slag powder in the liquid form. So, rho is something about, you can take it to be 3000 kg per meter cube. And viscosity, so it is a very viscous fluid, okay, temperature is not too high. This could be something around 0.3 kg per meter second. So, if you now put all these values here, okay, then you get the mass flow rate of powder, for example, is 3000 into casting speed is 1 by 60. Okay. This is 10 to the power minus 3, and this is multiplied by 2, and then this is (3,000). This is 9.81. This is 10 raised to the power minus 9, and this is divided by 12 into 0.3. So, you should be able to calculate this out, and this is (3,000) multiplied by, this is, you can say 10 to the power 4. So, 1 by 12. So, 0.8 multiplied by 10 raised to the power minus 4 plus, you can say 3, roughly speaking, because I have no calculator. So, I am doing roughly 3000 into 10, 3. So, this is about 30 into, okay, 10 to the power minus 12, and this is 12 into 10 to the power minus 1 into 3. So, roughly speaking, if you, this is 10 to the power minus 12. So, you can imagine that this term, if you look at the first term, which comes out to be something like 3000. So, if you say this is 10 to the power minus 1, so 0.08 into 3, that is what is the first term. So, it is about 0.24, and then here you can see this is 30 into 10 to the power 12, and this this term is going to be much smaller than this, almost negligible. So, this is going to be 10 to the power 9. So, this is already 10 to the power 11. So, if you multiply it, this will be 10 to the power minus 8, and this will go up. That will make it about 10 to the power minus 7. So, this term is really small. And then you can calculate that it is going to be the mass flow rate. That mass flow rate, because we had substituted everything in SI unit, it will come out to be kg per second, and this tells us about, for such a huge continuous casting machine having a width of 1200 mm, okay, the flow is something around 0.24 kg per meter cube per second or so. So, you really 0.24 kg is something like, if you multiply it by, so 240 grams per second. So, you can imagine that, if an operator is there who is throwing powder over the caster, it has to be done really at a very, very small rate. So, there are dispensers through which at a slow rate the powder really falls, and you will surprise that when everything is so big, it is moving down, but the powder flow rate is not really right, and most of the powder flow rate under the given condition is dictated by the casting speed. As you have seen, I have retained only this term and omitted this term. So, I have assumed that the powder flow rate is governed mostly because of the movement of the casting strand, because the strand itself is moving in such a small slow velocity. So, that is why it is not really very large. I have omitted this, but if you want to calculate it, you can substitute this. I have introduced a typical value. It is not a sacrosanct value. This is a very approximate analysis. Okay? And as I said, that to do a real life analysis of flow within the film, one has to deal the subject at a much more complex level, and that perhaps is not within the scope of this course. And why should I say not within the scope of this course? And I think it has not yet been amenable to very advanced level of research because of many things or many phenomena which are involved in the whole process, including the reciprocating motion of the strand of the mold, and then downward motion of the strand, solidification, and within the powder itself, the powder in contact with the mold surface is solid. On the other hand, the powder in contact with the liquid in the solidifying casting is liquid. So, the powder itself is in range of state. It is somewhere solid, it is somewhere crystalline, it is somewhere liquid. So, it is a horrendously complex process, and sometimes the mold goes down and then it reciprocating motion, it comes up. So, within the powder itself, there is a changing flow pattern itself. So, those sort of complexities which I have now dealt, I have just illustrated in a very simple term that if you do a shell balance within the within a section of the film, in that case we can have a simple expression, and based on this a first hand estimate. First hand means that I have made lot of approximations, but thoda bahut to idea hona chahiye ki kya hai kya nahi hai. So, that is the number I have generated. Okay? The exact value may not correspond to this, so do not try to apply this to an actual industrial process. It is just a demonstration for classroom exercise. So, we will continue tomorrow again, okay? And then we will discuss that what are the other rigorous framework for flow. In this case, there are a lot of other things also which need to be explained to you. I have just taken, for example, a segment or a control volume at the center part of the film, disregarding. So, I will show you that what are dimensionless numbers, what is the entrance region, that if one moves the control volume, what are the effects which one would like to see. And in that context, perhaps there are several terminologies, like for example fully developed flow, etc., need to be explained. So, this is just the development of the framework that I wanted to address today. So, you accept that there is a procedure called shell momentum balance. If one does shell momentum balance, one will be able to arrive at a mathematical expression which one can solve, and then one can find out the velocity field, one can find out the mass flow rate, one can find out the average velocity, and so on and so forth. This is just the beginning, and then we can proceed to develop more advanced frameworks and perform the analysis. That will be discussed in the next class.